Hi guys, and welcome to the second lecture for Chapter 1. Today we'll be going over what science is, and we're going to dive pretty deeply into the scientific method. So science is a rigorous way of testing ideas, observations, and questions about the outside world. So it involves making observations and asking questions. It involves collecting information as well as evaluating information to draw meaningful conclusions. And science is basically curiosity in a nutshell. It involves different people or scientists looking at something and becoming curious as to what its origin is. So we ask questions about the outside world, and essentially we derive ways to answer those questions, and that's going to be through the scientific method. Now, the scientific method is basically an empirical way of acquiring knowledge in a very robust sense, and it's categorized the development of science since at least the 17th century, so that's the 1600s. So this is a very, very well-tested method that is frequently used and employed over and over again in different scientific disciplines. And it's useful and it's persisted this long because it's rigorous, it's effective, and it's conservative in nature. And we're going to go over exactly how it's each of these things in the next following slides. Now, we're going to walk through how we go through the process of a scientific method with the example below, and we're going to follow this example all the way from the beginning of applying the scientific method all the way through to the end. Now, the scientific method and science in a nutshell begins with an observation and a question about that observation. So, usually scientists will observe something that is happening, some phenomenon in the outside world, and they'll develop a question, usually what's going on there? Why is this happening? And they then use the scientific method and the steps in the scientific method to evaluate possible answers to that question. So an example of this is an observation. For example, say that we observe two different types of animals or different animal communities that live in seagrass, those underwater grasses that are in estuaries, as well as in bare sand. So we're seeing different living animals in seagrass as opposed to bare sand. And so our question from there is this something that we're just observing, or is this an actual finding? So do different types of animals live in seagrass and bare sand, or is that just something that we're seeing at this moment? So we have our observation, we see something happening, we see a pattern that might be apparent, and our question is that pattern actually happening? Is this actually a characteristic of these two habitats, or is this just some observation that we are seeing at this moment? Now, next, we develop a hypothesis. A hypothesis is an educated guess. This is the best attempt to explain the observations given what little knowledge that we have about the outside world or in the context that we are looking at in this specific moment. So again, we have our observation. We're observing different types of animals in two different habitats, seagrass and bare sand. And then we have our question. Do different types of animals live in bare sand versus seagrass meadows? And we have finally our hypothesis. We are hypothesizing, so our educated guess is that yes, seagrasses have different animal communities that live in them compared to those that live in bare sand. So now we have our educated guess. After we have our educated guess, we then make predictions based on our educated guess, based on our hypothesis. So we have our hypothesis, we have what we think is going on, and there are going to be things that we can predict based on that hypothesis that we can then test. So our predictions are specific statements based on our hypothesis, which can be rigorously tested. And this is used to determine if a hypothesis holds up to scrutiny. And testing predictions about our hypothesis is basically an empirical way of evaluating if this hypothesis actually does stand up to that scrutiny. So next up we have our experiment phase, and experiments are mechanisms with which we use to test our predictions and by extension testing our hypotheses. So for our experiment in the context of this example is that we go out and we catch fish and other marine animals at seagrass meadows and at bare sandy bottoms. And we don't do this just once, we do this over and over and over and over again. And by replicating the experiment multiple times, what we do is we we minimize the chances that the result of that experiment would occur by random chance. Now, this is different from our observations. Some of you might have been thinking that, well, if you observed it the first time, wouldn't it be common sense that there are different animals in seagrass meadows and in bare sand? We already went out and looked at them. Why do we need to run an experiment? Well, the thing is that if you look at two habitats at any one moment, there is a certain chance that what you're seeing is just a product of random chance. Maybe just by some random thing that is going on, maybe some seagrass critters made it to bare sandy bottoms, or vice versa. By repeating the experiment multiple times over and over again, we minimize the chances that our findings will be influenced terribly by random chance. Now, so we catch all fish and marine organisms and animals at seagrass meadows and at bare sandy bottoms. Then we identify all of the species that were caught at each habitat. Finally, we compare the species and the animals that are found in seagrass meadows versus the species that are found in bare sandy bottoms. This is basically how we conduct our experiments in a nutshell. So next we have our results, and our results are essentially just the results of our experiment, and we can use our results and the statistical tests that we use to evaluate our experiment to either reject our predictions and our hypothesis or fail to reject our predictions and the associated hypothesis. Note that I did not say we can prove that it's true. An experiment and science in general can never prove a hypothesis to be true. This is where it goes back to how the scientific method is very conservative in nature. So a hypothesis can only be failed to be rejected. We can only say that, hey, based on our results, we cannot empirically reject that this isn't happening in the outside world. We can never prove something true. The best that we can get is that over and over and over again, we have failed to reject this hypothesis. So this is probably going on. Again, anytime that someone says science proved something this or that or the other, they are misunderstanding what the scientific method does and how the scientific method operates. So going to our results, we found that in seagrass meadows, consistently in every sample that we looked at, in every form of this experiment, remember we're doing this over and over again, we found in seagrasses that there are pipefish, seahorses, oysters, sea snails, sea slugs, blue crabs, and hermit crabs. Then we looked at the animals that like to live in bare sandy bottoms, and we found things like olive shells and olive snails. We found things like flounder and mullet and minnows. And we found that over and over and over again, seagrass meadows were very different from sand meadows. Seagrass meadows were very different from bare sandy bottoms. Now, based on these results, we cannot reject the hypothesis that bare sand has different animals associated with them than seagrass meadows. We can't say that that's true, but we can fail to reject that hypothesis. So, based on the results of our experiment, that will determine whether we either reject our hypothesis or fail to reject our hypothesis. Now, if we outright reject our hypothesis, say that for the purposes of this experiment, we found the exact same fish and animals living in seagrass as we did in bare sand, we would reject our hypothesis that different animals live in seagrass and bare sand. If we rejected our hypothesis, usually what we do is we go back and we form a new hypothesis based on this new information that will account for our observations. So we will create a new hypothesis and repeat a different experiment based on the predictions from that new hypothesis. Now, if we fail to reject our hypothesis, as in the case of this example, remember that we actually did find different animals in seagrass meadows versus those in bare sand habitats. If we fail to reject our hypothesis like we just did, we develop new predictions based on that same hypothesis, and we find ways to test those predictions. And this is the process known as validation or falsification. Basically what we're doing is we're finding new ways to test the same hypothesis over and over and over again. Again, we are trying to make sure that our observations, that what we found weren't just an artifact of random chance. We are trying to make sure that this hypothesis and the results that we have actually hold up to scrutiny and actually hold water. So we repeat this over and over again until we are rock solid that a hypothesis has never been failed to be rejected, and then we begin to accept the results or accept that hypothesis into scientific doctrine. So if we have tried to test a hypothesis in multiple different ways based on multiple different predictions that arise from that hypothesis, and we've never been able to reject it, then we can begin to incorporate that hypothesis into scientific doctrine. Remember, a hypothesis can never actually be proven true. If a hypothesis is repeatedly tested using different experiments and using different predictions associated with that hypothesis, and none of them have been able to reject that hypothesis, eventually we kind of give that hypothesis a promotion. And instead of calling it an educated guess, we call it a theory. A theory is a very well tested and very well validated hypothesis. Basically, we have tried every angle to make sure that this hypothesis holds water, and every time we do, that hypothesis is validated over and over and over again. And this is where we incorporate that hypothesis into scientific doctrine as a theory, and we begin to rely on that theory as the basis of future scientific work. This is how science progresses forward in society and through time. An example of a theory is the theory of evolution. The hypothesis of evolution was tested empirically over and over and over again, numerous times in thousands of different experiments by many, many people. And each time, the hypothesis of evolution continued to hold water. That hypothesis was never able to be rejected. And so as a result of that, we promoted the hypothesis of evolution to the theory of evolution, because that hypothesis had been so rigorously tested that and it was never proven to be false, that we began to rely on that theory or that hypothesis for the basis of future scientific information. And indeed, we do rely on the theory of evolution. A famous biologist who I am blanking on right now, a famous quote in biology is that nothing in biology actually makes sense without the context of evolution. And that is a perfect example of how once a hypothesis has been tested and validated through a multitude of different experiments, then we begin to rely on that hypothesis, or we begin to rely on that idea as a theory for the basis of future scientific work. Now, this is the closest we can ever come to saying whether something is actually true. And it should be noted that theories can and have in the past been falsified. Eventually, someone comes up with predictions that fail to hold up to scrutiny in a given scientific test, and so that theory is either outright rejected or that theory is augmented in the face of that new information so that it accurately reflects what is going on in the outside world. Usually theories get augmented, they don't actually get thrown out. If something has been tested so many times and it only fails to hold up to water in very certain conditions, usually that means that the theory is incomplete. It's not necessarily something that's not actually happening. A perfect example of this is the example of physics. In the 16 and 1700s, Newtonian physics dominated. Basically, Newtonian physics for the law of thermodynamics, first, second, and third laws of thermodynamics, the theory of gravity. All of these were very well-tested theories that had originally been hypotheses, and they had been tested over and over again, and they were treated as almost as if they were true for hundreds of years. Then Einstein came along, and with a series of experiments as well as different equations, he found that in very specific situations, specifically in areas where things are moving very, very quickly, then the effects of relativity take place, and we are no longer, the idea of Newtonian physics no longer holds water. The predictions associated with Newtonian hypotheses and theories no longer worked in certain situations. And so what Einstein did is that in a series of equations, he augmented the theories behind Newtonian physics to more accurately reflect the predictions and account for the predictions that he had observed in his very specific experiments and mathematical theories. So usually what happens is that if the predictions of a theory are able to be falsified, if an experiment does not hold if the predictions associated with a theory do not hold water in very specific situations, either that theory is completely thrown out entirely, or much more commonly, that theory is augmented to better reflect what is actually going on in the outside world. Now, if multiple theories and hypotheses begin to come together to provide a larger picture or a larger perspective, this is sometimes regarded as something called a scientific paradigm. A paradigm is a dominant scientific perspective that draws from multiple theories and multiple hypotheses within a given discipline. You can think of this as almost like the general picture behind a given scientific discipline. So the theory of evolution and the context of biology within the theory of evolution and several related theories basically is a dominant paradigm in certain facets of biology, actually most facets of biology. And it should also be noted that paradigms can be thrown out too. Just like theories, occasionally there will be theories that contradict one another, and theories that arise, or experiments that arise that contradict the larger predictions associated with a dominant paradigm. Basically, this is the larger version of falsifying a theory or falsifying a hypothesis. If there are occasionally experiments that etch away at the dominant picture of science at a given time, basically what happens is that dominant view is thrown out in favor, or augmented in favor of one that can better account for the results of different experiments or different hypotheses or new theories. Basically, it is augmented so that it accounts for the new, more realistic picture. And this is something known as a paradigm shift. The discarding of an old paradigm or an old dominant view of science for one in favor of what more accurately accounts for what we are observing in real time is known as a paradigm shift. A perfect example is a heliocentric model actually replacing the geocentric model. So way back in the 14 and 1500s, we originally thought that the sun revolved around the earth. And that was a dominant worldview in astronomy. However, a series of mathematical calculations and a series of experiments basically determined over time that the theories associated with the geocentric model consistently did not hold water. And the paradigm associated with the geocentric model, the fact that the earth or the sun is spinning around the earth, no longer held weight. In reality, what they were finding in multiple hypotheses and experiments and theories was that in reality, the earth revolved around the sun, and the earth was actually spinning on its axis, which accounted for the sun apparently going around the earth. So one dominant worldview, the geocentric model, was thrown out in favor of the heliocentric model, meaning that this earth revolves around the sun. This is a perfect example of a paradigm shift, and it happens all the time in science. Now, usually, again, very similar to a theory, a paradigm is not outright rejected. Normally, if there are theories or hypotheses and experiments that are coming into conflict with the predictions associated with a paradigm, normally it means that the paradigm is incomplete. So when we refer to a paradigm shift, usually when we don't completely throw out the old worldview, we change it. We take the parts that are probably accurate, and then we add things, or we augment that worldview in favor of one that can accurately predict and describe what we are seeing in real time. Now, the final thing that we're going to go over is something called the peer review process. And this is the process in which scientists ensure the accuracy of scientific work. Remember, again, that science is very rigorous and effective, but it is extremely conservative in nature. And this keeps us from leaning on claims that might not actually be true. Now, in peer review, other scientists will field check the submission of new scientific experiments and the results of new scientific experiments to ensure that they were done correctly and that their results and conclusions are valid. Basically, what scientists do is whenever they conduct an experiment, they will write up the results in a scientific paper, and they will send that off to a scientific journal for peer review. Once the scientific journal receives the paper, what the journal does is it sends that paper to multiple scientists in the same scientific field, and it says, hey, look over the methodology here, look over the experiment, look over their conclusions, make sure that one, their methods are reliable, basically that they didn't cheat. Two, that based on the results of their experiment, their conclusions and their logic are sound. So if, for example, a scientific experiment had all of their methods correct and they found that raspberries were different than blueberries, and based on that they were concluding that raspberries cured cancer, that wouldn't make sense. Their logic doesn't hold, so their conclusions are not valid even though their methodology was sound. So by looking at both the methodology, the experiments, and the conclusions from the experiments, they ensure that both the conclusions are based on sound logic, the experiments were done correctly, and thus the results of those experiments and the conclusions associated with them can be incorporated into the larger body of scientific work. Now, if a hypothesis or if a manuscript or scientific paper is rejected, or if they found that something was funny, they would reject that paper, and that paper would not be incorporated into scientific doctrine. And this way, we keep bad information from coming into the larger body of science. This is the process of peer review. Now, that is everything that we have for the scientific lecture. I know this ran a little bit long. I apologize for that. However, I hope you guys got a lot out of it. I know that things never being able to be proven true can be a little bit hard to grasp. So if you have any questions, please feel free to shoot me an email or set up a phone conversation, and I will be happy to answer any of your questions. All right, I will see you guys next time. Take care.